Okay. Welcome to our class of solid mechanics 2. Today we're gonna cover the chapter 9, which is about the thin wall shaft. First of all, we'd like to introduce the definition of a thin wall shaft, and we developed a torsion theory related to this thin wall shaft. Well, geometrically, the thin wall shaft is very complicated compared to just a simple circular shaft. But the theory, after all derivation, become very simple, much simpler than derivations of the circular shaft torsion theory. To drive the torsion theory of this thin wall shaft, we first need to define a coordinate system, which is very important. There are three coordinate system. First is the Z. Z is the shaft axis, and in this direction we apply a torsion, and torsion is applied to this shaft. Now, this thin wall shaft is a closed one. It's not open, closed thin wall, and the thickness T can vary. There are two more coordinate systems. One is the S. S is along this wall, and that is the coordinate S. And so this thickness T is a function of S, and which is not uniform. Thickness can vary. That's a very important point. And there is another coordinate which is the normal to this S coordinate and this Z coordinate. So N is the normal to this tangential S coordinate. So N is normal, and S is a hoop direction, which is along this thin wall, and Z is the axial coordinate. And I should say this is a T. This is a T. Okay, this is a T. And so this is a thickness in S direction. So T is a function of S, is not constant, which can vary. That's a very important point in torsion hollow thin wall shaft. Okay, that's the simple geometry of this thin wall shaft. And now we try to analyze this shaft, only delta Z, some small portion of the shaft, okay, delta Z. Again, this is a subject to a torsion T, and this will twist. And a twist, we can easily imagine that there will be some shear stress along this surface, the top surface. Okay, this, we don't know the magnitude, we don't know anything, but what we know is that this a shear stress will be along this surface, and basically this will be a shear stress, right? Shear stress. So shear stress, we can say shear stress is along this S, and also along this N, which will be further simplified. But this is basic definitions of all coordinate system and torsion and delta Z. Now, what we like to pay attention is that a small portion, if you look at the bottom, okay, this is the bottom part, and at the bottom, we also have a, we can say this thickness is a uniform through the delta Z. Now we are trying to look at these portions. Okay, this is the one we like to pay attention and try to drive some a theory. The most important point in this derivation is that these shear stress derivations. Okay. So let's take a look at that part. This is a tau. Okay, this is a tau, and this is also tau. This is a shear stress, and please pay attention to this coordinate system. Again, this is a M, and this is a S, and this is a Z. Now, as we noticed from here, due to torque T, the shear stress will be developed, which will be tau Zs. I will rewrite here, tau Zs. Why Zs? Well, this surface is the surface of Z, so that's why this surface of Z. And Ys, well, this is the direction of the S. So this is the simply tau Zx. This tau Zs is certainly can distribute from along this surface, right? That they can vary. We don't know yet, but somehow there will be some stress distribute along this surface. Now, a very important point in this observation is that this tau Sz is acting on this surface. Now, this is, we can call S surface because this is a S surface, and Z is the direction of the shear stress. So tau Sz, and there is another one which will be also tau Sz, but two different surfaces. Let's call this is A surface, and this is a B surface. So the shear stress in A, try to delete this part, and shear stress here is tau Sz, and the shear stress here is the also tau Sz. Now here, before we moving further, we like to define very important concept, which is the shear flow. Okay, shear flow. Shear flow. What is a shear flow? What is the difference between shear flow and shear stress? Shear flow and shear stress. What's the difference? Well, shear stress is what we know. Instead of sigma, I use the tau to represent the shear stress. So shear stress is tau, but what is the shear flow? Well, shear flow, we use the symbol Q, and Q is defined as the integration of the shear stress which exists along this, in this cross-section. We integrate this shear stress over the thickness, okay, over the thickness from here to there. So this, again, if we look at the top, okay, if we look at the top, this shear stress may be not uniform, maybe small or large, depending on the along the thickness. And here is the same thing. This is a tau stress, but the shear stress we define is the integration of this z through the thickness. Thickness is n, right? The n, and from here to there, okay, here to there. So minus t over 2 and plus t over 2. So shear flow is simply integration of the tau over the thickness, through the thickness. So tau, as you know, this is a Newton per meter square. So it's a force per unit area. And now shear flow, since it is defined and integrate through the thickness, and so this shear flow is a Newton per meters, okay? And so simply, since it's integration of the thickness, the shear flow can be defined as approximately, this is average stress, and this is a total thickness T, okay? So shear flow, you can say that average, this is the average shear stress and times thickness. Okay, you can say equal sign. Okay, so this is the important concept of the definition of this shear flow. Okay. Okay, so this Q again, shear flow is defined as the average shear stress times thickness. So let's say this is a real distribution of this shear stress like that, and the this will be average. Okay, this is a tau average, and times times this is a thickness T. So thickness T times this average can be defined as the shear flow. Okay, so shear flow dimension-wise is a Newton force per length. So to calculate the force out of this shear flow, and then the force, to get the force, you have to multiply the Q times some length. Length is the over this length, okay? Which needs to be understood to calculate the shear force. Okay, that's the definition of a shear flow. And now, it's an important point is that this now, instead of a shear stress, we can say there is a shear flow. At this point is a point A, and here is a point B. So point A, we have a shear flow QA, and here we have a shear flow QB. Now, because all the shear stress of this shear stress and this shear stress always same, right? Shear stress, if we look at the shear stress like that, always this shear stress, and I'm going to use this shear stress and that shear stress, always the same, right? This one and that is always the same. They have to be same because of the we need to meet some shear moment equilibrium. Okay. Now same here. Okay. I need to close this. Okay, so this is the Q point A. So now very important is that this is the shear flow exists on the top surface, which where the shear flow can vary. Now here, this is a QA and this you can say QB. Okay. And this length is delta Z. And let's take a look at all the forces applied in direction of a Z. This is a Z. Even though the shear flow exists on the top surface, which is in S direction, but again, the shear stress SZ is equal shear stress ZS. So this one, now this shear flow, okay, is all in Z direction. And this shear flow is all in Z direction. So if we consider this as a body and we want to consider equilibrium, okay, force equilibrium in Z direction, okay, in Z direction. And the force in Z direction is the QA times dZ. And another force in Z direction acting on this surface is the QB times the same length, delta Z. So if we look at all the Z directional force, we can say that QA times delta Z, that will give us the force. And another force, actually this is the a minus, so I would say this is a minus. And another force is the in the other surface where we have the QZ. Again, the length is the same as here. So QB times the delta Z, and that is the positive direction. So this has to be plus. And to be in equilibrium in Z direction, this total force needs to be 0. Okay? And now, very simply, this delta Z disappear, and we come to a conclusion that QA needs to be same as QB. Very simple conclusion that can apply to any cross section. In other words, let's say we have a session. We have a session like that. Here, there, QA or QB or any place, actually, if we consider equilibrium like that, we can consider equilibrium. We can pick any point. To log out. Where? Yeah, there is a quit. Okay. Now we are free of KakaoTalk. So Q is constant. Okay, is a constant, and which is a conclusions of a z-directional equilibrium. And Q again is a function of S. S is this direction, and is constant. Is it simple but very powerful observations, and which can be used in derivation of this torsion theory for thin wall shaft. Okay, please remember that shear flow is a constant. But keep in mind that, please, this thickness T is a function of S, is not, it can vary. So this is the, is not constant. Thickness can vary, but no matter how the thickness vary, the shear flow Q, which is which along the S, is a constant. Okay, so we have, this is the most important conclusion in torsion theory of the thin wall. Now, let's try to drive the relation between how much stress we get from this torque. This is a top view of this shear flow, I mean the thin wall shaft, and now we have this shear flow Q. What we observed again is that we have all the shear flow, which is the all same in any along this line. Okay, that is the conclusion, which QS is the constant. Okay, so you can just say Q. That's it. And now we try to find the relation between this Q and torque T, which we apply. We applied the torque T, right? And torque T will certainly causes this shear flow. So what will be the relations? That's what we like to drive. And let's take a look at a small length, delta S. Okay, delta S, where we have a shear flow Q, and this is the area. And so the torque T, delta T, which was a contribution of this shear flow, which apply acting on this delta S, is that delta T is simply delta S. Delta S is the length along this line, and shear flow. That is the what force which we already have relations. So this shear flow Q times delta S gives us a force, and now this is a vertical distance from this line. So this is the H. So we have to apply this H. Okay, this is H, and this is the force, and this is the force, and this is H. So force times this distance H will give us the this torque. Okay, this, I would say this is a delta F. Okay, so now we try to integrate all over the S, and which will give us the total torque T applied to this section. And so from this above, we have this and QS and H and delta S. So please pay attention to H. What is H? Well, H is again, we have a length where I mean, along this length, and this H is a distance from the center toward this line. From this, in this integration, the Q again is a constant along this length. So this Q will be simply out of integration. And now, what is H and delta S? See, this H times delta S. This delta S times the vertical length H. What's the geometric property of this quantity? Well, we do know that delta S times H divided by 2 will be the delta A. I mean, the A here is a triangle area is defined as the help of this delta S and H. Okay, so H times delta S is simply twice. I'll rewrite here Q times a twice of delta A. Okay, delta A. Delta A is this one. So imagine we integrate here. We will have another area and another area and another area and so on. So this will be simply twice Q and integration of delta A. And sorry, this is not quite right. So this one is simply twice in Q, and this is the area of this cross section. Okay, area of this cross section. Again, please, what is this A? A is the all these integrations. Okay, integration of this area closed by this thin wall shaft. If we consider thickness, this area needs to be clearly defined. Is it within, inside, or outside, or center line? Well, it doesn't matter that much, because we already have assumption that the thickness T is very thin. So it doesn't matter whether inside, whether outside. But to be consistent, let's say we have a center line. Okay, we have a center line, but you will see it doesn't matter that much. So anyhow, the torque T we apply is simply twice of Q. Q, is a uniform, but unknown. But we do know this is the uniform, N times A. So we knew Q was the constant, but was unknown and was caused by the torque T. Now, using these integrations, and this is the this gives us that, and Q is simply torque T, which we apply to this thin wall shaft, and divide by twice of A. A is again this cross section, okay, and Q is, remember, the average times T. Okay, this is the average times T. So this is the very important result, and since Q is the average times the thickness T, so this one, this tau, you can say that shear flow Q divided by T, and so total T torque we apply and divide by twice A and T. So tau average, which is a function of S, okay, S is like that. S is like that. But again, please remember this. Thickness is a function of S. And sometimes thin and sometimes thick. And this is a function of S. So tau shear stress will be a Q. Q is a uniform, right? And T can be function of S. And now this one, I'm rewriting this one, and I'd like to emphasize how the tau can vary, even though Q shear flow is a uniform. So T and twice A and T is a function of S. Okay. The most important equation is actually this one, okay? A shear flow, which is the uniform, and simply calculate by equation T over twice over area. And now, second derivation is about the angle of twist. This is an old slide. This slide was not quite clear, so I had another one. This looks much better. So anyhow, what we like to have is the angle of a twist. The angle of a twist is like d theta and dz. This one is the, last time we derived T of Gj. That was for the circular cross sections, right? So that was the equation. Now, what we like to derive is this d theta dz, but for the thin wall shaft. Okay, so to do that, first, let's take a look at this thin wall shaft, and this is the length delta dz, and let's take a look at this part, this much, and then under torque, this area has deformed to this way. And the most important deformation is the angle phi, we call phi 1, okay, phi 1. And on the top, if we look at the top, and this line move to here, which I will call US, okay, US, because this direction is S direction. And this is the, I will call delta DUS. And now here, this angle, I will call theta. See, theta here is that over the delta Z, how much angle we twist. So this is the angle we twist, delta theta. So what we would like to derive is how much this delta theta over this delta Z. That's what we like to drive in this thin wall shaft. So let's get back to this part, the definition of the shear stress. Shear stress is simply tau n g gamma, right? And gamma is the shear strain and tau is a shear stress. And using definition of shear flow, and tau t will be a gt, and this will be the shear flow q. And now in gamma, okay, gamma is the angle variation of this P1 and P1. And there will be not only this way, but may have this upper deformation. There will be another angle, but this can be cancelled out, which makes a little derivation complicate, but please, this P1, or P2, okay? P2 is the out of plane deformation. But I don't want to pay too much attention to this P2 because this P2 will disappear. But anyhow, this is the shear flow. Please remember, this is the simply stress-strain relations. Stress-strain relations. You know, this one was all about equilibrium, right? All about equilibrium. From equilibrium, we got these equations. That is very clear. Now, we like to use this stress and strain relation to drive the deformation. So this one, Q times GT, P1 plus P2, and please, this form looks a little different, but this is the basically nothing but shear stress and shear strain. This is the shear modulus. Okay, so P1 is this, and this distance is the simply what ds and ds, and this length is a dz. So P1 is a ds, dus, and dz, and P2 is the out of displacement. Out of displacement is like the upper displacement, and over the ds. Ds is the this coordinate. And now we like to integrate. Let's first divide by GT. So GT will come left hand side, and then integrate over the ds. Over the ds means here, and integrate all the way and back to our original position. Okay, integrate from here and all the way and back to original position. So we simply divide by GT. So Q divide by GT and integrate all of the ds. And now P1 is this and P2 is this. Okay, integrate. And this is an important step. And again, the Q is the constant over the S, and Q is out of integrations, and ds over GT. Now on the right hand side, now this is important. US, okay, what is US? US, if we look at from the top, this is the US, okay, this is a US, and there is a center of rotations, and this, again, as I mentioned, this is a d theta, and this is the, again, a vertical axis. I will call, previous, we call H, but it doesn't matter whether we call H or we call P. This one represent the vertical distance from the center of rotation toward this axis. So this dus, okay, dus is P times d theta. Okay, so this dus is a P times the d theta, and dz and ds. Now this term, duz, vertical deformation over the ds, integration ds. So simply starting from here to back to original position, duz starting, duz last, that will be the same. So this will disappear. So this mathematically is a little complicated. So I don't want you to be confused by this term. So please, this one is automatically disappear. But the most important part is the on this part, and this dphi okay, dphi okay, sorry, d theta dz is the out of integration, because d theta dz, d theta dz is the constant over the cross section out of integration, and simply p times ds, or you can say h times ds integrations. Similar to our previous case, remember this, similar to our h integration ds. What is this? This is the twice of this cross section A. Yeah, same here. So this will be twice of A. Please keep in mind that cross section of whole this area. So twice of A, this is A, and d theta dz, So Q ds over gt, and Q and dA, we divide QA, and so d theta dz, which you like to drive, is Q over twice A and integration ds gt. Okay, so this is the form we need to remember. Okay, so this is the form we need to remember that. Well, this is a little bit complicated derivation, d theta dz, and please, this q, remember this q was a t over twice a. So we can put this term into here, or you can just leave it there like that, q over twice over a and integration of ds gt. Okay. G, what is a G? G is a shear modulus along this S, and T is the thickness. So if this G is a constant, okay, if G is a constant, this will be Q twice A, and G will be the constant. And then this ds t, as we noticed, this can be a function of the s in general. Okay, so if the material property is a constant, which can be out of integration, but still the t thickness is a function of s, we have to integrate. If this even t is a constant, okay, if this t is a constant, this equation will be further simplified. So we can say that this t, okay, this t is a uniform and just integration of ds. Okay, ds, integration of ds, what does it mean? It means that the length of this along this thin wall peripheral. Okay, so so this one is the result. Okay, and now this all derivation can be applied to a thin wall circular shaft. Why not? So I'd like to compare between thin wall shaft, which we just learned, and like to get back to a circular shaft. Okay, this is a circular shaft on the top, which we can also have a hollow circular shaft, no problem, right? So this one is the one. And now this thin wall shaft is closed. Try to look at the same same shape, very thin, okay, very thin, circular. This is the inner radius. This is the outer radius, R0. And so if we compare the theory, and then let's see how they are compared each other. Okay, so circular shaft, we do know the shear stress is simply torque T times R divided by J. If thin, the J is defined what R integration with the square and dA. So if this is a thin, this one is simply say integration Z and dA. What is a dA? Thickness T and twice of pi and twice of pi, right? And then D, the R, just, sorry, this, for this thin, this is simply twice of pi, and dA, over the A means 2 times pi over thickness and R0. That is the A times R0 square, right? So you can see that this is the polar moment of inertia for the thin wall circular shaft, and simply we put this thing to here, and R is R0, and this is the shear stress from a torsion theory. Now, from what we learned, what we derived for the thin wall shaft was simply torque twice of the A divided by T. So A is simply, again, this A is the average radius is R0. So twice pi R0 times T is the, I'm sorry. Here, yeah, this is very important, and this A is not just this cross section. A is the cross section all over this, enclosed by this closed loop, right? So pi times R0 square. Okay, that's the area. And we put this thing into here, and we got this one. Compare this. Derivation looks totally different, but the result, as you can see, they are pretty much, the exactly same. And for the d theta dz, what we derived here was that here, this Q was the T over twice A, and put it here, and then this is the one we obtained, and this is the final form, dphi dz. And for the torsion theory, dphi dz is simply torsion divided by gj, and j is like that, and put it here, and this is the dphi dz. And as you can see that this dphi dz and this dphi dz is the same. So conclusion is that this is the regular torsion theory, okay, of the circular shaft, and this is the thin wall shaft, okay, closed one. So if this one is a thin, or this one goes to a circular, so this will be circular and thin. This will be the circular thin and thin, okay, thin. And as you can see that the conclusion is of course, is the same. Okay, this is nice comparison between regular torsion theory and thin wall shaft theory, and both theory can apply to a thin circular shaft, and the conclusion, the result, the shear stress and angle of twist will be the same, obviously. Okay, so that is the basically all theory we need to drive in these chapters. And we need to understand derivation procedures. Derivation is simply equilibrium. Okay, this is the all equilibrium, and this is the one we have. Okay, this one I don't like this slide. I got a new one which looks simpler. So this one is the stress strain, and there is some geometric deformation constraint which was here, but that is the very simple and will disappear. We don't have to worry about it. But my point is that in derivation of this thin wall shaft, we did consider equilibrium and stress strain and geometric constraint, and we got all the results for this, right? And for this. So please remember those two very important, very simple, right? I mean, considering all you know, complicated geometry section, but the result, as you can see, that is very simple. Okay, so that is all about the theory and content we would like to cover today. Okay, so tomorrow I like to go to a tool and which I just share with you. The tool I'm gonna share with you, I'm gonna show you it's called 3D beam. Okay, 3D beam is very powerful tools, and 3D beam was I share with you anyhow, I will cover that 3D beam tomorrow, and that 3D beam will be used to verify these all derivations and torsion and beam theory as well. Okay, okay. So I would like to close the class, and thank you, and hope to see you again. Bye.